Hello, everyone. My name is Katya Garmash, and I'm going to present to you our joint work with Anton Chishkov about a paper called Exploring the Effect of Null Usage in Source Code. We're both from Huawei, the Russian Research Institute in Moscow. So what is the paper about? It is about code smells, also known as anti-pattern, and these can be described or defined as patterns in code that indicate that there might be a problem in your code. And typically, such code smells are identified based on expert knowledge or developer experience, and they're typically motivated on a case-by-case basis. So there's no uniform theory to explain why something is an anti-pattern. So in this paper, we would like to take one step towards this uniform framework that would explain that something is or is not an anti-pattern. And we want our framework to be data-driven and use observational data only, so not rely on controlled experiments with people. And since this sounds like a pretty challenging goal, so we start with a very narrow scope. We concentrate on a very specific type of patterns, namely the null patterns. This is a notorious case of patterns in programming languages. It has been argued on multiple occasions that it's not a good idea for a language to have nulls. It's not a good idea to use nulls in your code. And some of the reasons include the fact that if you use nulls, you need to implement null checks in your code everywhere. You will have ambiguity of your methods, input and return types. This can give usage of null can give rise to fail-slow behavior and other things. So equipped with this expert knowledge, we can develop our method, data-driven method, and polish it with respect to the null case, and then maybe extend it to an arbitrary pattern. So how can we can formulate our research question in a general way as follows. Does code quality improve if one avoids using certain code patterns? And if we manage to empirically show that code quality improves if we don't use a certain pattern, then we conclude that this is an anti-pattern. As I said, in this paper, we use null patterns as a case study, and we study their effect on code complexity metrics such as cyclomatic complexity and cognitive complexity. And we use code complexity as a proxy to code quality, which is of course a very strong assumption. And we can reformulate our question in a more specific way. Does code complexity metric decrease if one avoids using null patterns? And I want to note here that if we do manage to show empirically that if we manage to answer our research question empirically, this will be probably sufficient to conclude that null is in fact an anti-pattern. But if we don't manage to show it, it's not necessarily that null is not an anti-pattern. There can be other code characteristics that can be influenced by null, we just didn't consider them. So this is one of the kind of limitations and challenge of this type of approach. So now, which specific patterns and metrics do we consider here? We consider 4 null patterns. So null check, it's if condition, which checks whether an object is a null. Return null statement, assignment of null to a variable, and passing null as an argument in method call. And we use 4 complexity metrics, each of which are easily computable from data. And 4 of them, each 4 of them can be computed at a class level, but only 2 are computed at method level. And these are the 2 levels of granularity that we consider in our empirical investigations. Okay, so now we have our problem statement and we have our patterns and metrics. And then what we could do, why don't we just compute a correlation, like use the concept of statistical correlation to answer our question. We could compute Pearson's correlation coefficients between the patterns occurrences, which could be formalized as binary variables, like a pattern is in code or a pattern is not in code, and and the other variable, correlating variable, would be the metric. And here are the results which we obtained. As we see, actually almost everywhere we see positive correlation. So we can conclude that yes, if one uses a null pattern, then it leads to more complex code. But then we can also think and a bit more and ask a question: is this observed correlation? Does it really result from a causal relationship between the two variables, or is it spurious correlation? So, for example, we can look at the class correlation coefficients and notice that they're actually a bit higher than method level, and in general, not in all cases. And that could mean, well, one could explain it as follows. Well, classes are typically longer than methods. So in a longer piece of code, there's a higher chance of occurrence of some pattern. Also in a longer piece of code, there's a higher chance that it will be get more complex. So number of lines of code could be just an explaining variable, and so we can conclude that there's no deep relationship between null patterns and code complexity metrics. And there can be other unobserved variables we just didn't think of. So that's why we think it's not sufficient to just compute correlations, and we argue to suggest to use an approach that uses causal inference to answer our research question. So, and in the next couple of slides, I will introduce just the very basics of causal inference, just because I don't assume familiarity with this theory, but it's actually a really nice theory, and I encourage you to read our paper, or better even to read the textbook about it, because it's really, really nice. So in a causal inference, you start with a model, a causal model, which describes a mechanism that generated your observed data. And here you can incorporate your knowledge and your assumptions, your understanding of the phenomenon that you're studying. And one very popular kind of causal models are graphical models. So these are directed graphs where nodes are variables in your system, and arrows are a causal relationship between them. So, and these are two very, very simple causal models, graphical models, which first one is really naive, where we just assume there's a direct causal relationship between null and the metric. And the second one is the one that I described, where we have an explaining variable in the number of lines of code. And why graphical models are so cool and popular is because you can, based on the structural property of the graph of your model, you can derive conditional independencies between your variables. And this way you can you can get an algorithm or a recipe to compute conditional probabilities, which can be useful for many purposes. Another important concept in causal inference, which is not specific to graphical models, is intervention. So intervention is when you set a variable to a specific value, irrespective of the values of the other variables in your system. So in our case, if we translate it to our case, we could imagine a hypothetical scenario, a hypothetical experiment where we prohibit developers from using nulls, and then look at the code that they produced and see the average and look at the complexity of that code. And likewise, we can consider another hypothetical experiment where we actually force them to use null patterns, and then again look at the target variable, the complexity of codes, and see how on average the two averages, how much they're different. And this formula just says that. And yes, sorry, in this statistic, this value that I just described in words is called the average treatment effect. Here, just to know that in graphical model, again, you have a really nice formalization of intervention where that modifies the original graph. And again, given the modified graph, you have an easy way of computing conditional probabilities. And therefore, you can have an easy way of computing this conditional expectation under intervention in average treatment effect. Okay. So again, we can reformulate our research question one more time, now specific to our theoretical framework. So the question is there a positive average treatment effect of using a null pattern on code complexity metric? So positive average treatment effect, that means that if we forced developers to use nulls, then code would be more complex than compared to when we wouldn't do that. And this formula just describes that. And final piece of math, which again, I don't really have time to motivate and explain, but I just have to show it to you, is the empirical estimate of this average under intervention, average of y under intervention of x. So if you look at the right-hand side and you look at this formula, you will see if you ignore the denominator px of z, then it will be just a standard formula for empirical average of y, right? But what does this p do? This probability is called a propensity score, and basically intuitively it balances out our data set, our sample. So it gives more weight to rare items that are less likely to be in this data set and gives less weight to very frequent ones, so that in the end we get a balanced sample and have a more correct estimation of our treatment effect, of our average. The final thing that I have to explain here is the Z. Z is called is a set of observed variables which are called backdoor confounders, and intuitively, roughly, these are variables that have causal effect on both X and Y. And so now we have this formula, and this is almost exactly the formula that I use in the experiments. In order to apply this formula, I need a causal model, and specifically I need to define, we already have the X, which is the pattern usage, and we have the Y, which is the metric, and we just need the Z to specify the Z, these backdoor confounders. And in the next slide, I will explain what we assumed. So our causal model of code production is as follows. On a very high level, we see code production as being influenced by three major factors. First one is the semantics or the functionality of the program that you want to write. Second one is the external conditions under which the code was produced, for example, like time constraints, budget constraints, person power, style guidelines, experience of developers, and so on. And finally, the third type of factor is the code written so far. So because a code development is an iterative process, typically you modify the code, source code, multiple times. So it's natural to assume that what already has been written in your code influences whether you use or not use certain patterns. That's why we also include it as a backdoor confounder in our causal model. And this graph, I will not stop on here, but this graph just summarizes what I just said. Okay, null and metric are variables of interest. Okay, so now we're ready for the final part, which is the experiments. So now we would like, as I said, we would like to apply this concept of average treatment effect to verify that null is an anti-pattern. As data set, we used like a series of trending GitHub repositories at the time, when we started it, written in Java. And the results in the data set on a method level contained around 250,000 items, and at a class level, it was around 60,000 items. And now these are the two tables, which just report the computed average treatment effect for every pattern and every metric. So as we see for the class level, we see a uniformly positive average treatment effect for the null check. But for the other three patterns, the results are not as consistent, and there's sort of a tendency towards actually a decrease in average treatment effect. So, and on complexity. So that means that on average, when we use these three patterns the complexity seems to go down. Now, if we look at method level, kind of the same thing holds. For null check, we have increase in average treatment effect. In the other ones decrease. Okay, so the takeaway is what I just said: positive ATE for null check, and for the other ones tendency for negative one ATE. Okay, so we could stop here and say, well, it doesn't work, or I don't know, or maybe like we say, oh, null check is an anti-pattern, and the other three are pro-patterns. But we decided to think a bit further, and relying on our understanding of the domain of this patterns that we're studying. So we thought that the presence of null check is and could be seen as an indication of a more like careful, more experienced development style. So if a developer already uses nulls and then he also implements null checks everywhere, it means that he's using nulls, but at least he's like aware of that. So on the other hand, we see a decrease in complexity when using the other three metrics. That could just be, the effect could be that it's not necessarily that the resulting code is less bug prone, is better. It's just that it's a convenient shortcut to like implement the needed functionality, but maybe this code is more bug prone and maybe it's bad in some other ways. So we decide, so ideally for this type of analysis, we would need a variable in our model, the level of experience of developer or something like that. But at this stage, we didn't have that access to that. We plan to do it in the future. But we still did a simple analysis. We partitioned the original data set into two subset. First one is which has null checks, so null check is greater than 0, and the other one where null checks are not present at all. And we just recomputed the same average treatment effects for the other three patterns. So again, at class level, what we see now is interesting, I think, because we see that for the subset, for each of the patterns, the subset with null check greater than 0, it's almost everywhere, or even everywhere, almost everywhere, it's positive treatment effect, average treatment effect. But for the subset where it's equal to 0, it's almost everywhere negative treatment effect. And for method level, it's about the same. Almost, no, not everywhere, but almost. Yeah, okay. So here, this slide just summarizes what I just said. At class level, null check greater than 0 gives positive effect for all the patterns, all the null patterns that we considered, and for the subset with null check is 0, we get negative. We have a decrease in code complexity. So so that's interesting. So the first result could be interpreted as like if the developer uses null checks and he's careful about it, then using more nulls actually leads to more complex codes, as we expected. For the other negative ATE could the developer didn't implement any null checks, so maybe it would be interesting to look into how does that affect other aspects of code quality, for example, the bug rate. And so we could just estimate this ATE on bug rate, something we plan to do soon. This almost concludes my talk. So these are just the summary for follow-up research. So as I said, we would like it be, this brings me back to the original point that I made, that not showing like consistent ATE like decrease or increase does not necessarily say that null is not an anti-pattern, or but it just may mean that we didn't consider the right metrics. So in the future, we plan to look at other metrics such as bug rate. And of course, as we noted, our model is not very expressive, is not good enough, and we want to include more developer features, project style features into it. We still saw some discrepancy between method and class level of granularity, so we want to look deeper into that and maybe consider other levels. We didn't really conduct any sensitivity analysis of our estimation, like how much the model influences our result or how much the data sample influences our result. And in the end, so once we figure out these things, we hope and we hope it could be used to as a way of discovery of new anti-patterns, for example. So if we have a method to extract patterns from code automatically, we would have also a method to show that this is a pro or an anti-pattern. And also another useful application of this method could be as preliminary research before conducting randomized control trial with humans, because this type of research relies only on like observational data, which is valuable on GitHub and other places, so it's really cheap. But randomized control trials are really expensive, so it's better to first polish your ideas this way and then move on to the expensive experiments. And this is the end of my talk. If you want to, if you have questions or ideas, you can contact us. Also, the second link is a link to the repository that we use to extract patterns and metrics. And the third one is something I have to still fill in, but I will put my code that I used to estimate all the statistics that I reported here. Yeah, thank you.
Katya, many thanks for the presentation. We have a few questions from listeners, and then I will ask my questions. The first one is, adding new null checks, that's the question. Adding null checks can be a side effect of security considerations, which is true. So the question is, not the question, the statement. So we would expect security code to include more checks of this kind,
Okay.
and because of that, to be more complex. So it seems to be like a logical consequence of the being more careful, right?
Okay.
Okay, that's just a comment, not a question. And there is a comment. So could your method be applied to other languages, not just Java?
Yes, for sure. Yeah, I think it's general enough to be applied to other languages, and we use Java just because it's just a popular language to study. It's used in many research papers.
And there's a question also, which kind of the same as I wanted to ask. Is it possible? The question is, can we use another design patterns? For example, use of goto statement. You know, goto statement in C and C++ languages, they're very actively used right now. So is it possible to apply your method of research to understand the impact of these patterns?
I think yes. That was the idea, is that you could use you can extract any patterns if they're easily detectable from data, from source code. Then you could apply this method. You can again estimate the average treatment effect on some metric that you're interested in. Yeah, apply the same method.
And you mentioned in your previous slide that it could be applied to different other metrics, other patterns. So how many do you think those patterns we can imagine that we can investigate?
I mean,
1, 2, 3, or 30, or 100, or 1,000. Yeah.
Like in the order of hundreds. I don't know. I think for one single pattern, it's easy to run this analysis pretty quickly. So yeah, it just depends on your computational resources. But yeah, of course, here the big challenge is to have a good causal generative model of code. I think that's a big bottleneck, big challenge of this approach. Yeah.
And do you think there could be some noise or some distraction in your methods? I'm just trying to challenge you. So maybe you can answer no, but that's maybe you found something which actually could be the possibility to add some distraction to the numbers. I don't know. Maybe tell us about it.
Yeah, for sure. So, I mean, the big challenge in causal inference of this type, at least, is that you assume, yeah, I didn't say it actually, but when you design your causal model, you assume that all these confounders that you identify, all these explaining variables, they're exhaustive. So there's no unobserved confounders, and this is a notoriously difficult thing to check. It's like impossible to check, basically. So yeah, so there can be always something that you didn't think of, which actually influences this observed correlation. And the way it can be checked, so there are different methods of sensitivity analysis, which, as I said, we didn't really invest in yet, and we should. So yeah, of course, there can be noise, and we have to be more careful.
And what do you think about the statement you started from, where you said that quality and the complexity are not, are pretty subjectively connected? Because obviously it's difficult to say what is quality, but you decided to use complexity as an indicator of quality. What other indicators maybe could be used in this case, or maybe it's possible to extend your research and use a number of indicators? What do you think?
Yeah, so as I said, I think bug rate if you have a data set where you have like labeled with buggy code, then that could be a nice, I think such data sets exist, so that could be a nice metric. Another metric maybe could be computational complexity, like, running time. If you have such data, like for a piece of code, how long it runs or something like that. Yeah, and maybe other kind of empirical metrics. I don't know. Yeah, I mean.
So now it's logical to claim that you found the connection between this null pattern and the patterns and complexity, not just quality, not quality, but complexity.
Yeah, complexity. Yeah. Mm-hmm.
So basically, the conclusion is that the more of these null patterns we use, the more complex will be the code.
Well, no, I'm not sure. As I said, it's a bit tentative, but yeah, in code that uses null check, it's the case. I can check.
Okay. Another question from one of our listeners: did you include a programming paradigm in your analysis? For example, functional style or imperative style?
Like, did I? No. You mean like as a explaining variable?
Yeah, probably.
No. But yeah, that's a good idea. Yeah, in general, we have to think. Like for now, if you look in the paper, we use really simplistic features as explaining variables. So that's really an area for a lot of research and improvement.
And how long did it take, the project?
So so it's based on the project that we ran at Huawei in our lab here. So that I don't know, ran for half a year. And the research part, like the final thing that I did with estimating the average treatment effect, that took, I don't know, 2 months. I don't know.
And the final question: do you think the results of your research will be heard by practitioners who write the code? Will they listen to this not recommendation, but your observation?
I think, I think for them to listen, it has to be more like substantial. For now, it's really very speculative, the conclusions that I made. So we have to work more for them to hear it. For now, I wouldn't rely on it if I were them.
All right, and thanks for your presentation. Thanks for submitting to the conference. Yeah, it was great talk.